Hello. Yeah, welcome to the introductory section or lecture of the operations research course. My name is Dr. Bright Upon Afum. So in this lecture, we will look at the history of operation research, the nature of operation research, a modeling approach that are employed in the operations research. History of operation research. So OR, operation research, actually began during the World War II. It's mostly attributed to the military operations during World War II. So what happened was that the war took more time to stop, and so most of the resources of the military personnel were running shortage, and therefore there was the need to allocate scarce resources. There was the need to allocate most of their machineries or their arsenals to the various fighting sectors. So the British and American military management actually called on a group of scientists to research into the military operations. So it is claimed that their efforts were instrumental in winning the air battle of Britain, the Island Campaign in the Pacific, the Battle of the North Atlantic, and others. So the industry after the war became interested in this field. So as a result of the apparent success of the operations research in the military, so the importance of the operations research became more apparent as a result of the industrial boom following the war, and also as a result of increasing complexity of organizations. So by 1951, operation research has taken its hold in the Great Britain and was in the process of gaining momentum in the United States. So two of the major factors that contributed to the rapid development of operation research were: one, there was substantial progress that was made early in improving the techniques. So most of the techniques that the group adopted were actually improved upon, and it was we saw that they saw much substantial progress in that. Then two, there was the development of electronic computers. Therefore, most of the problems could be solved faster using the computers instead of the human brain. And so it's contributed to the rapid development of operation research. The nature of operation research. Operation research is concerned with optimal decision making. So it's actually not looking at the best decision making, but it's looking at the optimal, that is the not best in quoted, but the most appropriate decision that must be made at that particular time. So it cannot, or it's not necessarily the best, but it's the most appropriate that satisfied all the various conditions that are affecting the decision variables, right? And also is concerned with modeling and deterministic and probabilistic systems. So is the system held constant, then is solved, or sometimes using probability, and also it could also be modeling or dynamic. And all this generates with real life systems. Operation research deals with the need to allocate limited resources. So always there is a need to find out the best way of doing something or the best way of achieving a particular resource. And that's what operation research concerns itself with. So it's used by the industry specialized in the aircraft and missile, automobile, communication, computers, electronic systems or electric power, food, metallurgy, in the mining industry, the paper industry, petroleum, transportation, business, financial institutions, government agencies, and even hospitals. So the techniques of operation research can broadly be classified into two main aspects. So basically, are they the MPMs or the mathematical programming models, or they are probabilistic? So the mathematical programming models provide exact solutions. Like for instance, 1 + 3 is equal to 4. So that is an exact solution. However, probabilistic models provide reasonable approximation of solutions. Like for instance, 1 + 2, then instead of 3, you say it's maybe 3 or around 3. So it can be 3, 4, or 2, or 3.5. So all those are probabilistic, or they are approximations. And so in terms of the MPMs, that's the mathematical programming models, it looks at linear programming and most of the extensions or the combinations of the linear programming models. It looks at PET or CPM. It looks at, we'll look at all this in extension and consequent lectures. So look at network flow. What do we mean by dynamic programming? What do we mean by game theory? What is integer programming and nonlinear programming? Then the probabilistic models looks at Markov chains and Markovian decision processes, queuing theory and applications, inventory theory, forecasting, reliability, decision analysis, and simulation. So what's the modeling approach in operation research? So it leads us to what is a model. So a model is actually a representation of a group of objects or ideas in some form other than that of the entity itself. So for instance, you want to study a real world system, then you represent it with a model or with another system that is easily understandable or that can easily be understood. So that is what we refer to as a model. So the real world system may be complex during observation, and we cannot actually experiment with that. But however, we will be able to represent the real world system with an object and refer to that object as a model, or with mathematical equations and refer to them as model, or with words and refer to them as model. Then we can do experimentations on that. So in terms of the representation of the models, there are three main types of models. We have the verbal models, the physical models, and mathematical models. So what are the verbal models? So verbal models are expressed, or they tend to express the real world systems using functional relationships between the variables in a word passage. So linguistics are mostly employed to represent the real world problems or the real world system. So verbal models are used extensively in the business world, and they have the advantage of being easy to understand. The verbal models can also be used to verbalize decision strategies from more sophisticated models. They cannot be experimented with. They do not indicate how outcomes or measures of effectiveness change with decision alternatives, and it is not easy to show how the relationships change with decision alternatives. Then the second type of model is the physical models. Physical models are very common. So they take on the physical appearance of the object that is being studied. So what that means is that we are studying about, let's say, houses or aeroplanes. Then instead of taking that big aeroplane to study, which may be very expensive, we build or construct a miniature physical aeroplane or building, and we subject it to all the other constraints that we are thinking of. and see how it affects or it relates or it translates those variables into the objective that we are looking for. So that is physical model. So it's normally used to display or test the design of objects like new buildings or new products. Now, physical models are used for experimentation, and they barely describe the problem or the system under study. So what that means is that it generates innovative design, alternatives for solving the decision problem. They are limited to solving relatively limited class of problems, mainly design or engineering problems, and they do not contain explicit relationships. So they are decisions that are making up or affecting the model. Usually you cannot see the relationship between those decisions. So definitely it relies on try and error method, and therefore is very time consuming and also very, very expensive. Then we have mathematical models. That's the third type of model. So this type of model expresses the relationship between or affecting the real world systems with mathematical symbols. So it's basically abstract, and therefore managers are unable to appreciate these type of models. So the real world problem is oversimplified using mathematical equations, like for instance, how the world or how vehicles move to cause accidents, maybe in how two vehicles collide. If you want to model it, then you want to grossly oversimplify it using mathematical symbols and also mathematical equations and inequalities. So the relationship between them are all represented in that way. You want to look at how pollutants in the water move from one place to another. Then you are using mathematical symbols to represent them, and even their relationship or their relations with the environment. So those are what we refer mathematical models. So the effect of different decision alternatives can be tested. So that's the positive aspect. So the variables that are affecting the decision variables or the decision objective, or that are affecting the main objective of the study, can easily be changed or modified so that we see its effects on the decision that must be undertaken. So they can also represent many complex problems efficiently and concisely, and in many cases provide the cheapest way to analyze problems. So it becomes very cheap, because there's no need to build a physical model, run your experiment on it, build another physical model, change the parameters, run your experimental study on it. So it becomes cumbersome if you physical models. However, mathematical is not. You just have to change the decision variables or the variables that are controlling the main objective, and then see its effect or impact on the objective. So mathematical models are therefore used more extensively in operation research. How then do we model operation research problems, or what's the approach that we use? So the first approach is that we identify the problem and we formulate the problem. So the problem is formulated mathematically, constructs a mathematical model in terms of the relationship between the various decision variables, link them to the external factors in terms of constraints, and also link them to the decision variable or the objective function or the decision that must be undertaken. Then we solve the model, or we derive solution from the model. When a solution is obtained, we test the model to validate whether the model is feasible, whether the model is applicable, whether there are any constraint that introduces different dimensions to the model. We have to test everything and then later establish controls over the solution. So there are 5 main steps in modeling problems in operation research. So we'll take them one by one. Formulating the problem. So the problem is studied and the relevant systems that are controlling the real-world system is studied, and we develop a lot of statements to be able to define the particular problem. So usually it's like using verbal models or translating the verbal models into mathematical models or mathematical problems. So they normally include determining the objective function. What is the main objective? Then also, what is the constraints? What are the restrictions on the decision variables or the objectives? Then what are the relationship between the decision variables, their environment, the organization? Are there any policy available? So possible alternative courses of action and time limits to make the decisions are all studied. Then after that, we construct the mathematical model. The model that will represent the problem. So a number of quantifiable decisions are made, and they are made to represent the decision variables. Like for instance, you want to use x1, x2, x3 up to xn as the decision variables, or you want to represent decision variables with x, y, and z. Any variable that you want to use to represent the decisions, that is fine. It depends on the researcher. And then we measure the performance of the model in terms of the mathematical function of the decision variables, which is called the objective function. So the objective of the problem or in solving a problem is also is linked to the various decision variables, and we call it the objective function. Then the restrictions that decision variables are subjected to, or even the objective function is subjected to, we also express them as equations or inequalities, and we call these restrictions as constraints. Then we derive the solution. That is, we solve the problem using any standard software package. Sometimes the work or the problem is so complex that the researcher has to code the algorithm itself, propose or develop his own algorithm to be able to solve the problem or to be solved by computer strength. Then normally, when we solve, we arrive at a solution and we refer to that solution as an optimal solution. We say optimal because it's usually not the best solution. Let me put it that way. It's actually the most appropriate solution that satisfy all of them. So best is actually put in quotation marks. So suboptimal solution or optimal solution actually refers to the most appropriate solution or most satisfying solution, so the solution that is satisfying all the constraints, right? So that solution can be the best, or usually it's better than it's actually not the best, but it's satisfy all the conditions. So I'm not using the best because when we are solving the operation research questions, you will see that there may be best solutions and there may be worst solutions, especially if you want to sacrifice some of the resources or decision variables that are affecting the problem. Now, the solution can also be suboptimal solution. That means that it's actually not the optimal solution, but we would accept it as a solution, which is good. For instance, the solution may be taking time. The computer is taking time to solve it. So instead of allowing the computer to spend all the time to solve, we can cap the time the computer takes to solve the problem and call it suboptimal solution. Or sometimes the solution itself is based on approximations, and therefore it is not an optimal solution, but it is good suboptimal solution. Then when we get a solution, then now we conduct post-optimality analysis in terms of after the solution is derived or is obtained, we want to check whether it responds to certain high values of the decision variables. So that is conducting sensitivity analysis or conducting parametric analysis on the solution. We'll look at all these things, right? Then the fourth one is then we test the model, whether the model is feasible, whether the solution is making sense. We test it so that we can validate the model using historical data, using predictions. We do that to validate a particular model. Then finally, we establish controls. We establish controls over the model. The controls may be putting some organizational operating procedures in place for implementation, building some, if it's a more fiscal model, building some controls in terms of switches that needs to come on to be able to activate certain protocols in the system. All those must be done. Or if there is a light that is showing on the system, then it means that something should be activated. So those are the controls that we do. If it's a software, are we identifying bugs? What happens if there is error and all those things? Do we need help manual to be able to work through the software system? So those are all some forms of controls that must be established. Yes, so that's it for the end of the introduction. So we look at the history of operation research, the nature of operation research, and modeling approach used in the operation research study. Thank you.